Hello everyone, and welcome to this session where we will use the structural analysis program Ftool to analyze the statically indeterminate truss shown in the figure on screen. The problem under consideration is stated using the United States customary system of units. I will briefly explain the hand solution using the consistent deformation method and the virtual work method before I solve the problem using Ftool. The truss is made up of 7 members and has 4 reactions and 5 nodes or joints. Therefore, the number of unknowns in the problem is 7 plus 4, which is 11, while the number of available equations is 2 times the number of nodes, which is 10. Comparing 11 to 10, the truss is statically indeterminate to the first degree. The truss is classified as externally indeterminate because the source of indeterminacy here is the extra reaction. Internally indeterminate trusses have additional web truss members, usually forming crosses, which is not the case here. The hand solution of such a truss involves choosing a support reaction as a redundant, drawing a primary and a secondary structures, then calculating all truss member forces on these structures in order to apply the virtual work formula to calculate the required deflections. These deflections are then used to write the consistent deformation method compatibility equation, which is then solved for the redundant. I will now demonstrate the solution procedure using the computer program. After performing structural analysis of the truss, I will ask the program to display the reactions, then draw the axial force diagram as well as the deformed shape of the truss. According to the question, we are to solve the truss twice. The first time by assuming that all truss members have the same modulus of elasticity and cross-sectional area. And in the second solution, we are to assume that certain members indicated in the question have double the value of E times A. We will initiate our Ftool program and then open the United States Customer Units template that we have prepared in previous sessions. If you have not watched these previous sessions, then I do encourage you to do so in order to keep up. Next, we will define our nodes. I will activate the keyboard mode and click on nodes. The first node will be at 0, 0, which will correspond to point E here on this figure. This point will have coordinates of 0 and 0, and the truss will span 40 feet in the X direction and 30 feet in the Y direction. So we're going to have the first node at 0 and 0, second node at 40 and 30, then 20 and 30, 0 and 30, and then this point here will have an X coordinate of 20 and a Y coordinate of 15, which can be obtained from similar triangles between the triangle BCD and the bigger triangle AC and E. So we have one more node to add, which is 20 and 15. If you don't see all the nodes on the screen, then please click on this icon here, which is Fit World on screen. Next, I'm going to deactivate the keyboard mode and start connecting these nodes to form my members. This is the first one, second one, third one, fourth, fifth, sixth, and seventh. The next step is to assign the material and cross-sectional properties to these members. By clicking on Material Properties, we can assign the material properties that have been defined in previous sessions to the selected truss members. If you don't know how to define a material and how to assign values for the parameters inside that material, please watch the previously recorded sessions. I'm going to click here Apply to apply this material to the truss members on the screen. Then I'm going to click on the section properties. I have already defined a section and I called it section 1. And here I've assigned a cross-sectional area and a value for the moment of inertia. Later on we will define these members as truss members, so the value of the moment of inertia is actually irrelevant here, but the program requires you to insert a value or it will not run properly. It will give you a signal or a message saying that some parameters are missing. So we're going to insert a value here, but you will see that it will not affect our solution whatsoever. So I'm going to select all the truss members on the screen and assign the cross-sectional properties here to all of them. The next step is to define our supports. If we look at the structure here, we will see that we have a pin at E and we have rollers at C and A. So we're going to start by defining the pin support at A. There's a roller support here, but I'm going to change the angle in order to show the correct orientation of the support on the screen. And we have another roller here, and again I'm going to change the angle to show the support correctly. The next step is the most important one. We have to tell the program that these members are truss members. If we do not specify to the program that these members are truss members, then Ftool will treat them as beams and will show shear force and bending moment diagrams for these members, and the shear force and moments will have values because the program will consider these members as beams. Now what we want to do here is to specify to the program that these members are specifically truss members, which are two force members. And that can be accomplished easily from here. Rotation release. There are two ways to perform this step. We can select all the joints on screen by clicking and holding the Shift key and then selecting the joints one by one. After that, we will tell the program that these joints are to be considered as pins, all of them. We don't really need to do that because there is an easier step. I'm just going to reverse what I did. And the easier method is to select the truss members themselves and then to ask the program to define these members as two force members, members that are pin connected at their ends. Both methods will give exactly the same result. Next, we want to define our load. By looking at the figure here, we can see that the load in this problem is a 9 kips directed in the negative y direction and located at joint B. So in Ftool, we're going to go here to nodal forces. I have already created a load and called it load 1. And here in the y direction, we will assign a magnitude of 9 kips, and the minus sign indicates that the load is acting downwards. So I'm going to select the node required and assign that load to this particular node. Now we are ready to solve the first part of the problem, where the modulus of elasticity and the cross-sectional area are constant for all truss members. That can be accomplished by clicking on the axial force diagram here. I'm going to reduce the scale on the screen a bit so that everything is visible, and I don't like these axial force diagrams, so I'm going to reduce the scale here to 0. In this way, we have a truss where every truss member is displaying the internal force acting on it, and the minus sign here indicates whether the force acting on the member is tension or compression. The reactions can be easily shown by clicking here on Display and then clicking on Reaction Values. This figure shows the reactions and the internal forces obtained using Ftool. Let's compare these to the values obtained using the hand solution. In this figure here, these are the values resulting from the manual solution. Let's reduce this one here and look at both of them. on screen, we can see that the internal forces in the truss members are identical. The deflected shape can be obtained by clicking on this button here, showing the deformed configuration, the scale of which can be changed from here. Remember that the deformed shape here corresponds to the material and cross-sectional properties that you have defined, and therefore I'm not going to show any values here in particular because the question did not assign a value for the modulus of elasticity and the cross-sectional area. So the deformed shape here is irrelevant in magnitude to this particular question. Had the modulus of elasticity and the cross-sectional area been introduced in the question, then we can come here and show the values on such diagram. The next step is to solve the second part of the problem, where it is indicated in the figure here that three members, which are AD, AE, and ED, these three members form this triangle here. These members have double the value of E times A. So we're going to solve the truss again by creating a new section and multiplying the cross-sectional area by 2. This can be done by going to the section properties, defining a new section, and then assigning a cross-sectional area that is twice the previous one. You remember in section 1 we defined a value of 5. Now we are defining a value of 10. Again, the magnitude of the moment of inertia is irrelevant here because these are truss members. And another thing that we really need to pay attention to is that the question did not actually specify values for the modulus of elasticity or the cross-sectional area. So what is important here is actually the ratio between the first cross-sectional area and the second, which is 2. If you divide 10 by 5, you get 2. So you can assign whatever value here and then multiply that value by 2. So we're going to select these three members. You can select the first one and then click and hold Shift while clicking on the other two. Make sure that section 2 is selected and assign the properties of section 2 to these three members. This is the only required changes. So now we are ready to observe the results. I'm going to show the results corresponding to the second part here, obtained from the manual solution. And by clicking on this button, we can show the results for the second part of the problem. Again, I'm going to remove the diagrams and just keep the values. We can reduce the size here and compare the results, where we will see that the results are again identical. The deflected shape for the second part of the problem can be obtained by clicking on this icon again to show the deformed configuration. Again, you can change the scale from here. This concludes this session. Thank you so much for being with me, and hopefully I will see you in the upcoming sessions. Best wishes.